Today, we're going to talk about one of the most important ideas in all of physics. It's also one of the most misunderstood. It's an idea that explains everything, from why time only flows forward to how life itself is even possible. It's called entropy. And to really get it, all we have to do is start with one super simple question. So, what does the Earth get from the sun? I mean, it seems like the easiest question in the world, right? You probably already have an answer in your head. Yeah, most people say energy or heat or warmth. And look, that makes perfect sense. We can feel the sun on our skin, we see plants using its light to grow. But that simple answer actually hides a really deep and fascinating puzzle. Because here's the catch. For the Earth to stay at a nice, stable temperature, not boiling or freezing, it has to send the same amount of energy back out into space that it gets from the sun. Think about it. If we just kept absorbing energy without getting rid of it, our planet would get hotter and hotter and hotter. So the energy budget has to balance. Energy in equals energy out. So if the amount of energy isn't changing, what is it that we're really getting from the sun that makes all of life possible? Well, the answer comes from a 200-year-old discovery, and it all started with someone wanting to build a better engine. All right, let's jump back in time to France right after Napoleon. The Industrial Revolution is in full swing, and the key to power, to everything, is the steam engine. And there was this young French engineer, Sadi Carnot. He'd seen France defeated, and he was convinced that the secret to restoring his country's power was to master the steam engine, to figure out the fundamental rules of how they worked. And boy, did he have his work cut out for him. Back then, the absolute best steam engines were just incredibly inefficient. They only turned about 3% of the heat they generated into actual useful work. Carnot wanted to know, what's the limit? What is the absolute best an engine can possibly be? So, Carnot dreamed up this perfect imaginary engine. He pictured heat flowing from something hot, which does work, like pushing up a piston, but then, to complete the cycle and get it ready to go again, he realized you have to dump some of that leftover heat into a cold place, like a reservoir. And he saw that this wasn't just some design flaw, it was a fundamental rule of the universe. What Carnot figured out was absolutely profound. To get any engine to do work over and over again, you have to throw away some waste heat. You can never, ever get 100% efficiency because some energy just has to be lost as it goes from the hot source to the cold sink. Now, in a real-world engine, it's even messier. You've got friction, you've got heat just leaking out into the air. The total amount of energy is still there, of course, but it spreads out. It dissipates. It becomes less concentrated. And because of that, it becomes less useful. And here's the key. This spreading out is a one-way street. You can't just magically gather all that lost heat back up again. Decades later, a German physicist named Rudolf Clausius finally gave this idea a name. He called it entropy. And he defined it as a measure of how spread out or how dispersed that energy is. The easiest way to think about it is like this. Low entropy means your energy is concentrated, it's ordered, it's useful. Kind of like the hot, pressurized steam in an engine. High entropy means that very same amount of energy is now spread out, it's disordered, and it's way less useful, like the lukewarm air in a room after the engine has run for a while. Clausius summed all this up in two beautiful, simple laws. The first law of thermodynamics says the total energy in the universe is constant. You can't make it, you can't destroy it. But the second law, and this is the big one, says that the entropy of the universe is always increasing. It's always moving toward a maximum. In other words, things naturally go from order to disorder. But why? That's kind of a weird thing if you think about it. Most of the other laws of physics work the same forwards and backwards in time. So why does energy only ever spread out? Well, the answer from another physicist named Ludwig Boltzmann is that it all just comes down to probability. It's just a cosmic game of chance. To get a feel for this, just think about a Rubik's Cube. When it's solved, it's in a highly ordered, very specific low entropy state. And what makes it so ordered? Well, there's only one way for it to be solved. Just one specific configuration out of all the possibilities. Now compare that to the number of ways it can be scrambled, over 43 quintillion. So if you just close your eyes and start making random turns, which state are you more likely to end up in? The one single solved state or one of the 43 quintillion messy ones? Yeah, it's not that some force is making it get messy. It's just that there are astronomically more ways for it to be messy. And that's exactly how energy works. It spreads out simply because there are vastly more ways for it to be spread out than for it to be concentrated. So now that we have this idea of entropy, we can go all the way back to the beginning. We can finally answer our question, what are we really getting from the sun? The answer isn't just energy. It's a constant stream of high-quality, highly concentrated, low-entropy energy. That's the secret sauce. The energy that gets to us from the sun is far more useful than the energy we send back out, even though the total amount is exactly the same. And here's the cosmic transaction. For every one high-energy, low-entropy photon that we get from the sun, the Earth radiates about 20 low-energy, high-entropy photons back out into space. And all of life, every plant, every animal, every hurricane, every single thing, we all exist in that gap. We take in that concentrated energy, use it to build complex things like ourselves, and in the process, we spread that energy out. You know, this constant one-way journey from order to disorder is what gives time itself a direction. It's the arrow of time. It's the reason we remember the past, but not the future. It's why we see eggs break, but never see them unbreak. The universe is simply moving from a less probable state to a more probable one, and we're all along for the ride. And this isn't just a local thing. This principle operates on the grandest scale you can possibly imagine. Our entire universe began in a state of incredibly low entropy at the Big Bang. Now, a smooth, uniform early universe might sound chaotic, but when you factor in gravity, it's actually the opposite. It's a highly ordered, low entropy state because gravity wants to pull things into clumps. And that's exactly what's been happening ever since. Entropy has been increasing as matter clumps together into stars and galaxies. And as you can see, the undisputed champions of entropy, the things that hold almost all of it in the universe today, are black holes, a discovery made by Jacob Bekenstein and Stephen Hawking. So think about it like this. When you pour milk into tea, the first moment, when they're separate, is simple. The final moment, when they're completely mixed, is also simple. All the beautiful, complex, swirling patterns only exist for a moment in the middle, as the entropy is increasing. Life, us, we exist in that fleeting moment of complexity. We are those swirling patterns in the tea, powered by the low entropy of our sun. We are temporary, intricate structures that are, in a way, just helping the universe along on its inevitable journey from simple order to simple chaos. So the real question isn't what we get from the sun, but what we'll do with this little bit of low entropy we've been given.